So it's a pleasure to welcome everyone to our Dean's Distinguished Lecture Series, something we do in the spring, which is to invite a prominent person, somebody who's really interesting, to talk about their work, talk about their research, their perspectives, and really allow us to learn more about them, see what they're up to, and also through the process of conversation, questions, for them to learn a little bit about us. Now, in the world, of course, that existed before 2020, these would be in person. We'd be all together, probably over in CAVC. Obviously, it's a little bit different this time, but nevertheless, the opportunity to gather, in this case by Zoom, I think is, still compelling. So it's my pleasure to introduce our speaker. And today's Dean's Distinguished Lecture will be delivered by Dr. Ellen Stofan, who's the Undersecretary for Science and Research and the John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. She started in that role in April 2018 and is the first woman to hold that position. So Ellen comes to the position with more than 25 years experience in space-related organizations and a deep research background in planetary geology that included being the chief scientist at NASA from 2013 to 2016, served as a principal advisor to former administrator Charles Bolden on NASA's strategic planning programs, helped guide the development of a long-range plan to get humans to Mars, and Mars is certainly in the news today, so that's pretty exciting. Worked on strategies to support, for NASA to support commercial activity in low Earth orbit as we transition from the International Space Station to sending humans to the Moon and Mars in the mid-2020s. Ellen earned her bachelor's degree in geology at the College of William and Mary, her master's and doctoral degrees at Brown, both in geological sciences. And then while finishing her doctoral degree, Ellen joined the Jet Propulsion Lab as a postdoctoral fellow and became the deputy project scientist for the Magellan mission to Mars. Her research focuses on the geology of Venus, Mars, Saturn's moon, Titan, and Earth. Our favorite mission was Cassini, primarily because of that interest in Titan. Ellen has published extensively, received many awards and honors, including the Presidential Early Career Award for Scientists and Engineers, and the NASA Distinguished Service Medal, and was also named one of CNN's Extraordinary People of 2014. I'll hand the microphone over to Ellen in just a moment. Let me remind anybody, as you have questions, put those in the chat. Marcus Herman will be picking those off, and then we'll work through as many as we can at the conclusion of the talk. With that, my pleasure to introduce Ellen to you.
Thank you very much. I really appreciate this invitation to speak here today. And to some extent, I feel like I'm coming to a family. There's so many people that I know at ASU. I saw a few of them coming in. I probably missed some, but I saw Dave Williamson, Steve Ruff, and Lindy Elkin-Stanton, and I have so many friends here. I don't want to start listing them because I'll leave people out. But it's a huge honor to be here and speak with you today. And what I thought I would do, I thought it would be interesting to do, is sort of start way back in the past and then sort of set the stage for where I think we're going in human exploration, and then come around at the end to sneak in a little bit about talking about what we're doing at the Smithsonian. So if I could have the next slide. Now, 2 summers ago, we had an event on the National Mall to celebrate the 50th anniversary of the landing on the moon. And when I look at this picture, which is the Saturn V rocket superimposed on the Washington Monument, and that's a whole other story on how we got permission to do that. But what really amazes me is over about 4 nights in July, commemorating the Apollo 11 landing, we had over 1 million people come out onto the National Mall, happy people. But now when I look at them all standing next to each other, one of whom was me down in that crowd, all I can think about is germs. So obviously the last 2 years, or especially the last year, have really changed our perspective on gigantic crowds. But I wanted to start here in this celebration of the Apollo 11 moon landing, because I think it reflects back to something I'm going to keep circling around, is sort of why we explore. What motivates people to say, we're going to send people to the moon? How do we accomplish this? How do we get it together? What motivates a society to spend that kind of money? And underlying this 50th anniversary celebration of Apollo, In days before COVID, when we didn't know how important the notion that Americans can do anything they set their minds to, that the celebration of that as we celebrated Apollo would become so important about a year later. I wanted to play you a clip from the show that we did on the monument and on those large screens you see in the lower left to give you a sense of what we were celebrating. So if we could go to the next slide and play the video.
New Eagle, turn back. Roger, how does it look? Eagle has wings. Okay, all flight controllers, go for powered descent. Retro, go. Fido, go. Guide, go. Control, go. Telcom, go. GNC, go. Ecom, go. Surgeon, go. Capcom, word go for powered descent. Eagle, Houston, you read your go for powered descent, over. Ignition 10%. Altitude will go high. Houston, you're looking at our Delta 8. Alright, affirmative. Flight alarm, looks good. Looking good, over. Accepting its guidance. 1202. Stand by. 1202. Right, retro. Go retro. Throttle down. 6 plus 2. Give us the reading on the 1202 program alarm. We have another 1202 alarm. 1202, what's that? If the executive overflow, if it does not occur again, we're fine. We're going that flight. We're going that alarm. Same type, we're go flight. Okay, we're go. We're go. Same type, we're go. Single alarm. Tell them to leave it alone and we'll monitor it, okay? Okay, 75 feet. Car's looking good, down a half. Rod. He's taking in his up H now. Rod. 60 seconds. 2.5 now. Straight shadow. 4 forward. 4 forward, just into the right low. Contact light. Okay, engine stop. Tranquility Base here. The Eagle has landed. Roger, Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Okay, we're going to be busy for a minute. Okay, keep the chatter down in this room.
Hatch reported coming open at 109 hours, 8 minutes, 5 seconds.
Okay, Neil, we can see you coming down the ladder now. At the foot of the ladder, the lamp footbeds are only depressed in the surface about 1 or 2 inches. And they'll step off the lamp now. That's 1 small step for man. 1 giant leap for man.
That is 1 small step for man. But 1 giant leap for mankind.
Dear man from the planet Earth, first step foot upon the moon. July 1969. Became a day for all mankind.
If we could go to the next slide. So, what we were trying to capture in doing that gigantic, ridiculous event on the National Mall was that inspiration piece, especially because, as most of you know, and certainly all the students in the audience, over half of the population of the United States was now born post-Apollo. So not people like me, who actually did watch it in my pajamas at that moment when it happened. But this idea of how do you bring this sense of accomplishment, the sense of, as humans, we can set ourselves again to tackle any problem that is in front of us. And so if you put aside all the economic and technological, geopolitical reasons for exploration, I do think that that inspiration piece is incredibly important. And I like that to frame a discussion of human spaceflight. And as we think about why we explore and how we explore, I love to come back to that. And one of the things that I want you to think about, especially as I come back to at the end of the talk, and we're talking about getting humans to Mars, is it was 8.5 years from Kennedy's speech at Rice University where he said, and it's, by the way, that speech is in a larger video that is just a clip of it. It's called Go for the, if you Google Go for the Moon, Smithsonian, you'll find it. It was 8.5 years from that Rice University speech to us landing on the moon. And remember, when we went into that, we didn't have spacesuits. We didn't know how to have life support systems in space. There was so much that we didn't know. We didn't know how to navigate to the moon. And so the idea that in 8.5 years, we went from that point to actually landing humans on the moon is really an incredible accomplishment. Of course, we spent an awful lot of money, 4% of the US federal budget across the years of Apollo. Nevertheless, we were able to accomplish amazing things. And I also think it reflects, and again, thinking about this as we are now poised to think about sending humans back to the moon and onto Mars, the kind of risk posture that we took, doing things like Apollo 8, a mission that was not intended to go circle the moon and come back to Earth. It was originally just intended to go into Earth orbit and do some practice, but we were concerned we were falling behind the Russians. And so they decided, oh, let's send Apollo 8 to the moon, and they did. So also a whole different interesting discussion around the willingness to take on risk. If I could have the next slide. So fast forward now 50 some years later, 52 years later, obviously that lunar program ended. It wasn't sustainable. But on the other hand, it did give us the shuttle eventually the ISS. But also what happened in those intervening years, which it was driving me crazy, always to say, oh, NASA went away between Apollo and now. NASA did not go away. NASA was doing amazing things, not just in the human spaceflight program, but of course, exploring the Earth, exploring our solar system, the universe, our sun. And to me, one of the most shattering things in a total revolution in science that's been happening for about the last 10 to 20 years is this issue of exoplanets, finding planets around other stars. This is just a map of some of the planets that were discovered by the Kepler Space Telescope. And especially important, those blue to green dots that you see on there that are the Earth to Neptune sized planets that are in the category that we think could hold on to an atmosphere and thus potentially be a candidate for another Earth. So shattering understanding of just about every star we see in the night sky is likely to have a planetary system around it. The fact that we've discovered many, many, many multi-planet systems, and the fact that we are now starting to have the technology, especially as we move towards the James Webb Space Telescope and some of the very large Earth-based telescopes. We're going to be studying the atmospheres of these planets around other stars and really trying to get closer and closer to understanding whether we're alone. Can we find Earth 2.0? But of course, then this has made us look back at our own solar system and really think about how ubiquitous is life in our own solar system. If we're trying to figure out how ubiquitous life is in our galaxy, in the universe, well, maybe life on Earth isn't unique even in our own solar system. Next slide. So as we've thought about that, one of the things, and as we've discovered all these exoplanets, one of the things I really like, and this is a slide by Don Brownlee, that's one of my favorite slides to show, because as we start looking for that Earth 2.0, you really start thinking about what is it that we're looking for. If we're looking for Earth 2.0, and all of these depictions here are what we think the Earth looked like at some point in its history. Obviously, bottom center, we have our beautiful blue dot, ocean planet. But to its left is snowball Earth, which existed in one time. We have cyanobacteria Earth, and of course, my personal favorite, magma ocean Earth, up there in the upper left. So when we're going out and looking at other Earths, as a geologist, frankly, I'm excited about finding some of these past Earths so that we rely on models to really understand, and yet knowing that we're developing all this telescopic technology that's actually going to be able to allow us to study these various stages of Earth's history, I think is particularly fascinating. Because if we've learned nothing else, and I'll be coming back to this a couple times, about habitability. Habitability isn't just a place. So it's not just saying, all right, we found a planet this distance from this star, but what we understand from our own planet and increasingly from our own solar system, habitability can be a time period, not just a place. Next slide. And that's really shown in our own solar system when we've thought about habitability, you know, starting out with something like, oh, it's the habitable zone, the distance out from the sun of a planet where water could be stable on the surface. So that makes us think about, well, Venus at some point could have been in that habitable zone in the upper left there, Mars obviously in the lower right, and obviously I'll coming back to talk about Mars quite a bit, and Earth. And fascinatingly, as we pushed our study of places like Venus, and it's been in the news even in the last couple of years, knowing that very early in Venus's history, we're fairly confident that Venus had an ocean's worth of water. Most of that was probably subsequently lost. Some of it is probably tied up in the interior, but how long did that period on Venus last before it went into its runaway greenhouse state? Could Venus have been habitable for some point in time? And you have people like my colleague, David Grinspoon, who's even suggested that there could be extant life on Venus in the clouds. I'm a little bit more of a skeptic, but we can't rule it out at this point in time. So thinking again of habitability is not just a place, but potentially a phase in a planet's history that could come and go. It's important to understand this in our own solar system as we are now collecting so many other solar systems to study. I'll come back to Mars in a bit, but the three bodies, other bodies in our solar system that I've put on this slide are fascinating because they're far outside that habitable zone that we talk about so much. Europa is the little gray ball in the middle, and you're looking at the south pole of Europa, where over the last decade or so, we've determined that there are cracks there. There's probably the subsurface ocean of Europa that erupts out into space that we are potentially going to study with the upcoming Europa Clipper mission. On the far right there with the plume erupting from a crack in the surface is Saturn's moon Enceladus. Also with the subsurface water ocean, we flew the Cassini spacecraft right through that erupting plume and determined that it was water that was coming out. There were also salts in it, there was silica in it, suggesting there could be subsurface eruptions taking place, maybe features like black or white smokers like on Earth's ocean floor that are thought to be potentially one of the early habitats for life. So Europa and Enceladus, huge targets of interest because of these subsurface oceans. So as we followed the water, trying to understand potential other locations for life, these two moons in the outer solar system have been of particular interest. I'm just going to dwell for a second on my favorite moon, which is down there in the lower right, Titan, moon of Saturn, only moon in the solar system with a substantial atmosphere. The bright dot that you see there at the top from Vim's data from Cassini is a reflection off of a sea at the North Pole called Punga Mare. And indeed, Titan is the only other body besides Earth that has open bodies of liquid. It rains, you have rivers that flow into seas and lakes, especially in the North Polar region. But given that Titan is in orbit around Saturn and that it's about 90 degrees Kelvin on the surface, that working fluid is not water, of course, but it's liquid methane and ethane. Which brings me to a really fascinating issue that I'll come back to in a minute of, do you need water for life? What if you had a different fluid? What if it was, say, liquid hydrocarbons? Could that actually be a substitute? So Titan is a particularly interesting place, I think, to go in our solar system to really understand what are the limits of life. Does it have to be water-based? Could it be different? And so Titan is particularly fascinating. I spent about 5 years of my life proposing a boat to send to one of those seas on Titan. That mission ultimately didn't get selected, but next slide. This mission did. I'm a co-investigator on this mission, which is led by Zibby Turtle. It is called the Dragonfly Mission. It is to send an octocopter. I can't speak, octocopter. It'll launch late in the 20s, arrive in the early 30s at Titan. And it will fly around in the equatorial zone, looking at some areas that were previously where the surface had been wet is now dry, flying in this dune region that you see, and then ultimately flying to an impact crater. And again, helping us to address this huge question of what can a place like Titan tell us about potentially what are the limits of life? And by going, out to Europa with Europa Clipper, going eventually, hopefully back to Enceladus, going to Titan, we're really pushing on this question of, is there a second or even a third origin of life in our solar system? How similar is it to life on Earth? And then how can we take that information and turn around to really fundamentally not just understand the nature of life itself, but to give us a better understanding of the likelihood of life beyond our solar system. Next slide. And that brings me back to the whole question, which I started with, which was human exploration. What role do humans play in this search for life beyond Earth? And so if you start with that argument that we certainly only sent humans to the moon because of geopolitical tensions, it had nothing to do with science, it had nothing to do with amazing things like searching for life beyond Earth. I do argue that this major question that has really solidified over the last 15 or 20 years with this data of exoplanets, with our knowledge of the body of other bodies in our solar system and their potential for life, this question of Mars being the most likely place beyond Earth, in my opinion, where life is likely to have originated, and the importance of humans to that search, I think is a critical driver of human exploration going forward. Is it a driver enough? We can talk about that. This mission, the NASA Viking mission, which arrived at Mars in 1976, is one of my favorite missions because my dad was actually in charge of the two rockets that launched the two Viking spacecraft to Mars. And it was where in 1975, to date myself, I decided that I was going to be a planetary geologist and grow up to be just like Carl Sagan, who I met at that launch. But Viking obviously took the next step that had been known from previous flyby data of Mars, had been known from telescopic observations of Mars, that yes, indeed, a lot of the surface of Mars had been covered or carved, by running water in its path. There was evidence of standing water from that data. There was evidence of running water from that data. Not a surprise, but huge confirmation from the Viking mission. And of course, Viking was sent to search for life on Mars. It had an experiment that was as well designed as what we knew at the time to understand how to search for life. And it got a negative result. And many people felt like this sort of killed Mars exploration for quite some time. What's fascinating today, and I have a lot of astrobiologist friends who I've heard speak about this, we didn't design the experiment right, frankly. That experiment was never going to find life on Mars. That doesn't mean there's not life on Mars, either in the past or even extant life. But we didn't know enough about Mars, and we actually didn't know enough for searching for life on Mars to have designed that experiment right. And so it's a fascinating issue of be careful what you're looking for. And I'll come back to that in a minute. Next slide. Well, obviously we've kept landing on Mars over the decades. And as our landers have gotten more sophisticated, going from just static landers like the Viking landers to mobile landers where we can actually rove around on the surface of Mars, our questions about Mars have been becoming more and more and more exact. I mean, you've got amazing data and again, a huge legacy of people from ASU involved in Mars exploration and in refining the questions and in gathering the data in a whole NASA philosophy called follow the water. Can we determine the history of water on Mars? How long did it persist on the surface? Was it present in conditions that were not too chemically strong, not too acidic, that had the potential for life to originate. So this question of, was Mars habitable in the past? And this whole series of missions, both landed missions that you see from over the years here, as well as certainly a huge richness of orbital data, have gotten us to the question of, yes, we now understand from about 3.5 to about 4 billion years ago, the surface of Mars was wet, maybe intermittently at times, but it persisted for long ago, and that the building blocks of life, things like amino acids that have been delivered everywhere in the solar system by asteroids, by comets, those would have been present on the surface of Mars. At one point, it had a fairly significant magnetic field that would have shielded the surface from radiation. The atmosphere was denser, of course, to allow this water to persist. So habitable conditions existed on Mars. But does habitable mean inhabited? Of course not. Next slide. So one of the things that the astrobiology community has been thinking about, and of course with that experience of the Viking lander experiment, make sure that when we go to the surface of a planet and look for life, that we're really thinking about what it is we're trying to measure, what it is we're trying to detect. And this in general, I would argue, still follows a general path, but not completely. This is something NASA's developed on their astrobiology website. You can go and look at it if you're interested, called the ladder of life. So what are we looking for in increasingly complexity to be able to go to a surface with a spacecraft and eventually with a human and say, have we found life on another planet? Is it life as we know it, or is it potentially life as we don't know it? Are there significant differences? And so where we are on Mars right now is unfortunately still down there in the lower left. General indicators, Mars was habitable. Okay, that's huge. Actually, it took us decades to get to that point, and it's really important because if we can't check that box off, we can't continue up the ladder. So what are we doing now? Well, and I'll get to a little bit more of this in a second. Then you move on to looking for things like biomolecule components and then functional molecules. Can we find something that looks like DNA or RNA? And then as you get more complex, you could say, you know, does this is what I'm looking at, is there evidence of metabolism? Is it using something up to get energy and then excreting something else? Do we see growth and reproduction? Obviously, ultimately, do you see Darwinian evolution? Next slide. So as we've designed things like the, oh, Ariel Anbar is here. Amazing stuff. Please go to the and again, I feel like I'm talking to the people here who actually did a lot of this research. So the Curiosity rover has actually taken us a little bit further down that path, because what some of the mass spectrometer on the Curiosity rover has been finding fragments of organic molecules. Obviously, the surface of Mars is now not protected from incoming solar and cosmic ray radiation, which breaks up organic molecules. So you're finding pieces of organic molecules. Now, those could just be leftover, components that came from an asteroid or a comet. So just from meteorites, which we've seen plenty of strewn around on the surface of Mars. So we don't know those fragments are Martian, but it's given us enough of a hint for people to say, all right, this is at least positive. We need to keep exploring. We need to find more. And obviously Curiosity, as some of you know who actually work on Curiosity, it's still doing well. We're still gathering data. And I particularly love this shot of Gale Crater, because as a geologist, looking at those layers of rock and knowing that each of those layers of rock that you can see is telling you about a section of Mars history, and all we have to do is have the time to go and look at all of them. But frankly, this is the kind of slide that also makes me as a geologist think about how critical humans could be to the discovery of life on Mars, because I want to go in and interrogate every single one of those layers. I want to sample every single one of those layers. And a human can do that much more efficiently, much more quickly, get the specimens back to a lab, thin sections, start looking for this evidence of past fossil life on Mars. Next slide. So at this point, our latest accomplishment, and you have people like Jim working on this, is landing Jezero crater. Obviously, the Perseverance lander landed here in February. And again, a really wonderful combination of using orbital data, those colors that you see there, indicating minerals on the surface that formed in the presence of water. So knowing there's long-standing water in this delta region. So this is a great place to target the next lander, looking for the next evidence of life and really pushing beyond Curiosity. But one of the points I wanted to bring up for both Curiosity and now Perseverance, which is a similar designed spacecraft, both of these spacecraft weighed about 1 metric ton. We estimate, and I'll come to this in a second, we estimate to get humans on the surface of Mars, it's going to take somewhere between 20 and 40 metric tons. And for those of you who are familiar with how Curiosity and Perseverance landed on the surface, very complex system to slow it down as it enters the atmosphere, protect it from the very thin, from how much it heats up in the thin Martian atmosphere, slowing it down through a complex system of parachutes and retro rockets to the amazing sky crane system that then drops it onto the surface. Very complicated system, 1 metric ton, a huge challenge as we move forward. Next slide. And of course, I have to talk about Ingenuity because it's, first of all, so much fun. And you know, they didn't totally plan it this way, but could you get better names for a pandemic than Perseverance and Ingenuity? Because frankly, that's what we've all had to rely on for the last 1.5 years just to kind of make it through a week. And so I love that these names and the fact that they've worked. You know, it's just been an amazing month or so, and huge congratulations, obviously, to the team that put together Ingenuity. I was not an early fan when I was at NASA of the helicopter because it was so critical to make sure that Perseverance stayed on track and to make sure the sample caching system, which I'll get to in a second, was done well. But I tell you, the Mimi Ong and the group at JPL who's put this helicopter together are truly, truly amazing. And it also makes me reflect. And there's been a lot of comparison to obviously the first human-powered flight on Earth in 1903 to here we are just about 120 years later, the first powered flight on Mars. Really exciting. And I am obviously insisting that a future astronaut bring Ingenuity back so that we can put it next to the Wright Flyer in the Air and Space Museum. Next slide. So that sample caching system, which I think, I mean, actually Minnie Wadwas is hopefully on, but obviously a good friend of mine here at ASU. This issue that one of the most important things Perseverance is going to be doing is caching some samples of particularly interesting areas that it goes to that are potentially most linked to hopefully evidence of life on Mars. Those will be put in caches for a future mission, a Mars sample return mission, to come back to the surface and return. Now, this is really important as we think about humans to Mars, because obviously that round trip aspect, you got to go there, you got to bring them back. Practicing that with a Mars sample return mission is really critical. And for both Curiosity and Perseverance, both of these missions are testing technologies. In the case of Curiosity, doing things like measuring the radiation environment, really critical to getting humans to Mars. So we're already seeing the human program at Mars and the robotic program coming together to work together to get ready for a future human Mars mission. You know, this is going to be tough. We've obviously, in a planet, you know, of this size, which still small, but nevertheless still sizable, so a gravity well, and with an atmosphere, having to launch off the surface, return a sample to Earth is no small endeavor. And NASA is obviously working on finalizing plans with this that Minnie's involved with, that I think will be a critical step for later this decade, probably in partnership with our international partners. Next slide. So as we start talking about human exploration of Mars, I think it's important to really think about what are the huge challenges that lay ahead of us. But let's reflect back to that 8.5 years that it took from Kennedy's Rice speech to actually get humans on the surface of the moon. And I'm going to argue, which people can argue against me, that none of these challenges are actually as big as, or the unknowns certainly as big that we faced in the Apollo program. And so while everything I'm going to talk about is a huge, tough challenge, that doesn't mean that it's not solvable, and frankly isn't solvable. You know, people have asked me, well, when can we get humans to Mars? We can get humans to Mars as soon as we spend the money to solve these problems and go. That's all the time it takes. But that's a big if, right? You have to spend the money and do the technology work. So I would argue it's like an accordion. The less money you spend, the more it's going to stretch out in front of us. And the more money you spend, the shorter the time gets. And my frustration, which I'll probably come back to several times, is my entire career, and it's now almost nearly 30 years in planetary exploration. We've been 20 years away from landing on the surface of Mars. And right now, if you ask anybody, they'll say we're about 20 years away from landing on the surface of Mars. We're actually not. It could be sooner, or it could be longer, depending on whether we want to spend the money or spend it on something else. But it is hard, and I don't want to negate that there aren't challenges. I mean, I talked about the mass problem, sort of 20 to 40 tons. People need a lot of stuff. We go places, we take stuff with us. And Mars would be no exception. You obviously need a place to live. You need supplies. There's huge logistics issues, tough. Also power, you're going to need a lot of surface power. How are you going to accomplish that? It's a very dusty place on Mars. There's perchlorates in the dust. That's going to be a challenge to make sure that humans don't start breathing in that dust. Solvable problem, but a problem you've got to address. Of course, the deep space radiation environment. And then there's the issue that when you're at Mars, the communication round trip time can be as much as 44 minutes. So there's no longer really a good option for Houston, we have a problem, because you might have to wait 44 minutes before you can actually have an exchange of information with mission control. So things like artificial intelligence are going to be really important, because by the time an astronaut's gone 6 to 8 months to get to Mars, you're not going to necessarily be in the best mental state to cope with emergencies. So having good artificial intelligence, machine learning on board is, I would argue, just as critical as solving some of these other problems. Next slide. So how are we attacking all these problems? And this is, I'm getting, you know, once you're around for a while, you get to have slides like this. Is a vintage slide. So this is a slide. This was how we were thinking about getting to Mars during the Obama-Biden administration. And I would argue we're actually still basically on this same path, with uncertainties just like we had back then on exactly how we're going to do each of these. Obviously, right now, we're still what we called at the time Earth reliant. We are still in low Earth orbit, doing a lot of important technology work, which I'll get to in a minute, to get ready to go to Mars. Moon, back then we called it the proving ground, and the moon has obviously been the focus under the Trump administration. Just a few weeks ago, they announced the issue around the human landing system, which they selected SpaceX for, but there's an ongoing role. What is the role of the moon? How much time do you want to spend at the moon? What do you want to do at the moon? Where do you absolutely have to test the technologies? So are you going to, in the great words of The Clash, are we going to stay at the moon or are we going to go? And how long are you going to stay there? How much emphasis and investment are you going to put there before you go on to sending humans to Mars? Next slide. So the International Space Station, really critical for solving some of those challenges, and obviously the top one being human health, but lots of other ones, especially around life support systems that we've developed on the International Space Station, continue to perfect. Understanding of how the human body responds to long periods of microgravity. And then how do we make the human system more resilient to that? So artificial gravity would be great. We're nowhere near that. So given that the humans are going to spend so much time in microgravity, how do we keep them healthy over the long run? That's what we've been doing for the last 20 some years on the space station, and have really gotten to us to the point where we feel pretty confident that we can keep humans healthy long duration in space. Next slide. So one of the big activities that will happen next is something called Gateway, which is a small station, hopefully one that will serve as a model for a transfer vehicle that would get humans from the Earth to Mars, in orbit, probably a fairly large orbit around the moon. So we could use as a transfer point down to the lunar surface, but we could continue to test those systems, those life support systems. A working toilet is probably the most important thing to space exploration. We want to make sure that we have that on the way to Mars. And so testing those systems further away from the Earth, becoming Earth unreliant, is a really critical component of Gateway. Huge, also way to have a lot of international involvement in this, getting humans from back to the moon and on to Mars, and also critical for studies in human health, especially around radiation, because out in that orbit, you're outside the Van Allen belt, you're now subjected to both solar and cosmic radiation as you would be on the way to the moon. So doing a lot of research around radiation mitigation. Next. The first mission to test NASA's main systems are the Space Launch System and Orion that will get humans eventually back to the moon. Well, the first uncrewed demonstration is something called Artemis 1 that will happen in possibly November of this year, possibly slightly later. And this is the first step then in using this heavy lift launch vehicle, which you absolutely need. And right now the SLS, hopefully as it comes online, will be the only heavy lift launch vehicle we have. Hopefully we will soon have others. And the Orion capsule. And the Orion capsule is really important because you need heat systems, because when you come back from the moon and then eventually from Mars, you're coming back to the Earth at a much higher rate of speed. And you need heat shield systems that can protect a capsule re-entering Earth's atmosphere. So really anxious to see Artemis 1 take place and start testing these systems. The newly announced SpaceX human landing system actually relies on the SLS and Orion as part of its system. So that's an important capability that we need to have ready. Next slide. So how do you translate this whole going to the moon into actually getting to Mars? And there's been lots of architectures that have been put forward. I just picked one. This is one that JPL came up with in 2015. It's a short stay concept. But it still takes 6 launches of the SLS. Again, because of that stuff problem, you need to pre-position gear before humans get there. You need to have the systems. You need to have their return launch vehicle with them. So they regarded this as sort of a low-cost architecture for that first human landing on Mars. So there's lots of questions when you're putting together Mars architectures. Do you start with an orbital mission where you could teleoperate a rover that could go into areas where there could be water close to the surface and thus extant life that you want to keep humans away from? Do you do that as a first mission? Do you go right to landing humans on the surface, which is such a huge challenge? But I think as anyone moves forward with Mars architectures, the most important thing is to think about sustainability, because that's what happened at the moon is we lost the sustainability of moving humans out beyond low Earth orbit. We came back to low Earth orbit and stayed there for quite some time. And I think as everybody is working on these architectures, one of the things they're constantly trying to think about is how do we actually have humans moving out beyond Earth in a sustainable way for the long term. And for that, there obviously has to be benefit. There has to be some kind of economic benefit. There has to be an inspiration benefit. There has to be a technological benefit. Next slide. But I think one of the most important things for me, again, is to stay focused on the fact that hopefully within the next 20 years, someone is actually going to be seeing this view, which is looking at the Earth from the surface of Mars. This is from Curiosity, but still someday there will be a human getting this same view, looking back, hopefully having spent a day looking at fossils on the surface of Mars. But again, it's going to be an ongoing debate over the next 10 to 15 years that I think is going to be really interesting. How long do we stay at the moon? How much investment do we put on returning humans to the moon versus moving humans on to Mars? For me, the driver is science. I want geologists on Mars finding life. For other people, they have different drivers and they have different focus. And so to see how that debate plays out over the next decade or so is going to be interesting. Next slide. I wanted to, in my last -2 minutes, so I'm going to try to zoom through this, talk a little bit about Earth. Next slide. All of you are well aware that one of the things the space age over the last 60 years have given us is an awareness of what's happening to our planet. Obviously, the data we've collected from space have been able, along with ground-based data, have certainly shown that the planet is warming. And collecting these data, understanding them, is incredibly important, especially as we move into an era where we need to become more and more resilient to the effects of climate change that are already happening. Next slide. One of my, one of the interesting things, Catherine Hayhoe, who talks a lot about acceptance of climate change, it's really interesting. This is data from the Yale Climate Center. Most of the people in this country actually now accept that climate change is happening, but only about 40% of them think that it will affect them personally, which I find really interesting. There's sort of and you see the difference in the data. People along the coastlines are like, yeah, no, we get it, it's happening to us. Everybody else doesn't think it's going to affect them personally. And of course it already is affecting them personally. Next slide. One of my favorite programs that NASA has is called Severe. It's in partnership with USAID, where we go around the world and help people use Earth observation data to become more resilient to the effects of climate change. Really important, because obviously climate change affects the most vulnerable peoples around the world, including the most vulnerable people here in the United States, disproportionately. Next slide. Certainly at the Smithsonian, we are laser focused on the effects of climate change that we see from experimental forests that we have in areas around the world through a program called Forest Geo, from marine habitats, as in places down below off the Chesapeake Bay, where we're looking at things like how do seagrasses help store carbon? How do these nearshore and coastal environments, how do forests, how are they being affected by climate change, by human activity? But also, how can we then work to make them more resilient as we move forward? How does species reintroduction? It actually turns out you can reintroduce species and restore ecosystems easier than we thought. Marine protected zones, we're out there measuring, they actually work. If you create marine protected zones, the species actually come back. So how do we use data, both space-based and Earth-based data, to understand how to make this planet resilient to the effects of climate change while having to worry about things like zoonotic diseases and disease vectors that are changing because of a changing climate? Next slide. And of course, because we're the Smithsonian, a big part of our role is things like deep time, which Lindy is also in, talking about the fact that catastrophic climate change has happened in the past, it's happening now, working with local communities like we do here in Washington, DC, to move environmental justice forward, and of course, trying to create curriculum and programs to get scientific information out to the public. And the last slide, I just want to end on one of the things that I spent a lot of time on at the Air and Space Museum, just last slide, please, was really thinking about, as we move forward, when you talk about finding life on another planet or battling climate change, one of the most important things to me is to make sure we've got all hands on deck and are really tapping in to the talent of all people. And so in that sense, everybody knows who the Wright brothers are and who was on the Apollo 9 crew. But I want to make sure that everybody knows who Bessie Coleman is, the first African-American woman to get a pilot's license. I want to make sure they know Eileen Collins, the first woman to command a space shuttle, her inspiring story, or about the young American immigrant Shasta Ways, who flew around the globe and by herself. These stories, these inspiring stories, to make sure that every kid sees themselves in this grander exploration initiative, is really critically important. So thank you all very much, and I'm happy to take some questions.
So thank you so much, Ellen. That was fantastic. So interesting. Let me introduce Marcus Herman. He'll direct the questions. He's the chair of our executive committee, and it's the executive committee who goes through all the people we could possibly invite, does all the outreach. So they did all the work to make this happen. So with that, Marcus, I'll hand it over to you.
Thank you. Thank you for the talk. In the chat, there was, well, now there are a couple more questions that came in. So the first one is from Kohinoor Kar. He asks, hypothetically, if there were lives on another planet or moon somewhere, would it go through similar evolution processes as they occurred on Earth?
There would be some similarities, but I think it would be actually it's a great question, right? Because you think of evolution in general responds to environmental stresses. That's one of the stresses that causes it. But it depends on things like your eyes develop because of light levels. Some of our body systems develop because of temperature and weather and all those different factors. So if you start changing them, species could adapt in different ways. And we even see that across the face of the earth, where different species have found different adaptations to different environmental stresses. And so this is, to me, one of these so amazingly interesting questions, and why I actually do think it takes humans on the surface of Mars breaking open a lot of rocks, because finding evidence of life, saying, yes, I found one example of a single cell, okay, yeah, it's going to change everything and it's really meaningful. But for science, we want to know, how complex did that life get? Could we identify any different environments that caused that complexity to occur? How does that compare potentially to evolutionary processes that have altered life here on this planet? So incredibly fascinating area. And I think astrobiology is going to be one of those fields that over the next 20 years we're going to learn so much, and it's going to be amazing.
Let's go to a live question. Robert raised the hand. If you want to unmute yourself.
Thank you. Thanks for letting me unmute. Hi, thank you for the fantastic talk, first of all. I thought you made a very interesting and poignant point in the middle of it about the rate limiter really being about funding on national level at national scales. What's the plan? I guess that's my big question. NASA has a lot of, the most fantastic outreach materials out there. The dramatic pumping music of when we watch the 7 minutes of terror of the Sky Crane landing sequences. It's pumping out lots of really great imagery. How does that translate into the national funding in people's eyes for those working there? Do we need to call our Congress people more, apply more pressure? What's the actual trajectory there?
It's a really interesting question, because if we go back to the fact that during Apollo, NASA was 4% of the federal budget. NASA right now is about 0.5% of the federal budget. And if it went crazy and went up to like 0.7 or 0.8% of the federal budget, NASA would be able to do incredible things. But we all live in this world at this moment, right? And we understand the pressures on the federal budget right now, incredible pressures from COVID to the economy, to that whole existential, incredible threat of climate change that's looming over all of us, that requires incredible investment. So I would never go and advocate that NASA be 4% of the federal budget. That's, but 0.5 to a little bit higher maybe. And so I really think it is looking at what is the plan, what's the best use of NASA resources. But I do think it's important, if the public supports NASA, the public has to let their elected representatives know that. It's really important. But I think we also always have to keep it sort of in balance, right? Because the federal government does have a lot of priorities. The point I always come back to, because I encounter a lot of people who say, why should we spend money on NASA at all? And that was the advantage of growing up with a dad who worked for NASA. I had people saying that to me in 4th grade. So I've been honing these arguments a long time. Is this issue of we spend the money here on Earth. We don't actually launch dollars up into space. We invest them in the US economy, in good jobs. We move the economy forward. And we push technology forward. And obviously NASA has huge books they release every year of amazing technological spinoffs. And I think what's encouraging right now is when I showed my vintage Obama-Biden plan, that plan was more or less adopted by the Trump administration. And right now, what we have heard, I was on the transition team. We're not supposed to talk about what we did on the transition team, but what you are seeing, at least in the early days right now, is a lot of support from the Biden-Harris administration supporting that plan. NASA is a 10 to 20-year agency that lives in a 2-year town. And so that continuity of purpose for NASA is actually, to me, one of the most important things, maybe even more important than the funding level, is just not have NASA seesaw between different priorities, different targets. This Moon to Mars plan works. Now, the devil, as I also said, the devil's in the details, right? You can spend all your money and never leave the moon. Not a fan of that. Some people are. Or you could be like me and kind of spend a couple of minutes at the moon and then go to Mars. You know, but there's a lot of differences of opinion. And to me, what's the best use of resources? Where do you need to go to test the technologies?
Okay, the next question from the chat from Ahmed Ewaisha. Do you expect any kind of major collaboration between SpaceX and NASA to solve some of the challenging problems instead of them competing?
They don't compete. NASA, SpaceX is a NASA contractor. They don't compete at all. SpaceX has hugely moved exploration forward by doing things like making sure they can recover their boosters to bring down the cost of space exploration. But NASA and SpaceX partner. That's why SpaceX is part of commercial cargo, part of commercial crew, as we just saw last week. They've been selected to be on the human landing system, and they work very closely together. I do think there's a huge misconception about NASA being in competition with the private sector. I would argue NASA is in partnership with the private sector, and it's trying to figure out what should the goals of NASA be. Sometimes those are aligned with the private sector, and sometimes they're not, and that's okay. But NASA is a government agency. It needs to stay focused on its priorities, which are the priorities of the US government, but they may not be the same priorities of a private company.
Okay. Live question, Steve Ruff raised the hand. Steve, go ahead.
Hi, Ellen. So you almost addressed what my question is going to be with regard to SpaceX. But you didn't directly. So SpaceX is sort of the elephant in the room regarding humans to Mars and Mars architecture. And you didn't include anything about SpaceX Starship and what essentially is the goal of Elon Musk and SpaceX, which is to get humans to Mars. So there's a direct, I guess, a direct kind of goal of both NASA and SpaceX to get humans to Mars, and Musk is planning to use the Starship. What is your view of that? And you didn't refer to Starship at all with regard to Mars architecture.
Yeah, that's because Starship doesn't exist yet, right? It's great, it's on its way. And if anything we've seen out of SpaceX is they do what they say they're gonna do and they deliver. And so I am incredibly optimistic about what SpaceX is going to do. And I think what you're gonna see over the next, hopefully 5 to 7 years, is that 2015 architecture that JPL put together, that the only time when they put that architecture together, the only thing in town was SLS and Orion. At that point, right, in 2015, Starship, Musk had maybe talked about it, but it was not. Okay, they're testing some systems, it looks intriguing. You have other companies talking about future potential heavy lift launch vehicles. NASA needs to see them, as you well know. NASA needs to see them. It needs to see them tested. It needs to see them at least at some degree of reliability before it builds it into an architecture. However, the JPL architecture hugely suffers from inflexibility, right? It relies on one rocket. Big mistake, right? We all want to see architectures that rely on multiple rockets from multiple sources, because that's going to give you the flexibility that you need to actually get humans to Mars. So I'm more optimistic that as we go into the next 10 years, we're going to start seeing Mars architectures that are actually, in my mind, a lot more resilient, and therefore a lot more achievable, and then a lot more sustainable, so that we don't just go to Mars once. We actually have a scientific base on Mars where we can do the kind of science that we want to do.
There's a related question from Tony. Why plan for a return trip from Mars? Surely there must be qualified people who would sign up for a one-way trip.
Well, there are people who'd sign up for a one-way trip. Mars is, I think people totally underestimate how horrible Mars is. And, I'm someone who looks at images of Mars and wishes I could stand on the surface, and Mars is horrible, right? The radiation on the surface is incredible. The soil is contaminated with perchlorates that would kill you. Lack of oxygen. Yes, there's water. Are there Mars bugs living in that water? We don't know. In the ice, at least on Mars. It's not ready for prime time. It's not ready for humans. And, you can talk to private companies that might send people on one-way trips, but NASA brings their astronauts home. And that's what the plan is to do.
Okay. Next question from the chat from Tina Sindwani. How long will it take to get samples back from Mars?
Well, Minnie is a better person to answer that than I am at this point, but at least some of the architectures they've been looking at. So Perseverance will cache the samples. I think the plan I'd heard was for, they're looking at 26. I think some people have said 24, but it's more I'm trying to think if it's even years or odd years. Let's see, what year is it? We just got to Mars we launched in 20, got there in 21, so it is even years. So we would launch in 24, 26, or 28 are really the options for sample return, 6 to 7 months there. You'd have to spend some degree of time. If the sample was waiting for you in orbit, sorry, I'm thinking this through in my head because I can't remember the date. I think we're looking at a sample coming back in sometime between 28 and 30, optimistically.
Okay. Sandeep, you had a question? You could unmute. Still muted. See if I can.
Okay.
Now you're on.
Yeah, I was really glad. Very nice talk. I was really glad you mentioned AI, and we are renewing our school to have augmented intelligence. So was curious, what is the state of use of AI or augmented intelligence in space exploration, and what kind of decision making would be you foresee can be attributed or given to AI or augmented intelligence?
It's still pretty limited. The Perseverance rover used a relative terrain navigation to help pick its own landing site. So I think that's been NASA's kind of most leaning forward they've done. But I'm really, when I envision what that would look like, which I usually call friendly how, that you would need is really being able to say, all right, you have a human landing system approaching for Mars, and you get a series of different warnings, a series of different alarms. And again, unlike the 1202 alarm, which executive overflow has to be the best term ever, when you have a series of alarms, the humans, you can't really frankly trust the humans to deal with multiple inputs at a time like that. So you really are going to need the systems to be able to juggle alarms, to be able to make actual decisions, abort, not abort, what to do, what's a recommendation, what's a path. And so I think you're going to have fairly sophisticated systems that we're not there yet. But I think we need to start doing the work now and really think about what are the scenarios that you would come to. We do know that humans, after spending long times in isolation, have slower reaction times. All right, that. So my question would be to you, how would we compensate that with augmented intelligence? And so I think it's a really fun area, and it maybe scares people less than thinking about other uses of AI. To me, it's something we need to start working on because we've got to be ready for this. The humans are important, but we can't rely on them when they first get there.
Thank you. Yeah.
So let's move to the last question from the chat from Kevin. At this point, which country would you say is in the best position to reach a human-landed spaceship on Mars first?
All countries, because we're not going to do this by ourselves, and we can't afford it, right? We can't afford it, and we wouldn't want to. So when you look at something like the International Space Station, where you have countries from around the world contributing, when you look at something like Perseverance, when you look at how we're planning for a Mars sample return, no one country is doing this. Yes, NASA is leading because NASA has a way bigger budget than everybody else. NASA makes investments that no one else can make. But we need all hands on deck. We need people from around the world. We need their resources to help offset the costs. And to me, there's huge symbolism also in doing this as an international community, not one country. So that first mission to Mars, the first woman that steps out of the capsule, I hope she's American. But after that, it's going to be an international crew.
There's actually one more question. Could you elaborate on NASA's efforts in manufacturing in space? Particularly, how do you see R&D directions evolving and morphing in the future? A question from Bruno.
Yeah, it's a great question, and it's a whole area that I'm really interested in. And I actually had some notes I was going to talk on about it, but I saw I was going to go way over, so I cut that whole part out. This issue of low Earth orbit, and is low Earth orbit a future economic zone? With things like on-orbit manufacturing, and not just for space. So not just manufacturing large aperture telescopes that in space in situ that we need, but are there actual applications? People have looked at optic fiber that you can do much more purely, drug manufacturing. Is there an economic there? And I think what we're going to see, my theme is the coming decade's going to be crazy. The coming decade's going to be crazy because we're really at a point where NASA's going to have to say, we need to start turning away from low Earth orbit, because NASA takes a big chunk of money and spends it on the space station, commercial cargo, commercial crew. If NASA wants to go to the moon and then on to Mars, they're going to have to take some chunk of that money. Unless they get a giant budget increase, which we don't think is going to happen, they're going to have to take some part of that low Earth orbit money and start spending it on deep space human exploration. So is the private sector going to come in behind them? We all know the private sector only does what there's a profit motive for. So are we going to find a profit motive in low Earth orbit? In space manufacturing is one, beyond just space applications. Again, potentially the most things that have shown them the most promise are in just a few areas. But what I would like to see over the next sort of 5 years is let's really push this. We only have the space station for so long. Let's really push whether there's a there for the private sector. Let's support it. Let's see where it goes. Because at some point, NASA's got to say, we've got to turn our attention elsewhere, and with our attention goes a big chunk of our money.
Okay, thank you for all the detailed answers. Kyle, you want to wrap it up?
Yeah, so Ellen, thanks again so much. Let me remind everybody who registered, Christine should have sent you a link. There's immediately kind of an open forum, continue the conversation, just some relaxed Q&A. Please click into that if your schedule permits. If you didn't get that link, please send Christine a note. Christine, any logistical issues you would also want to address here before we conclude?
I think Christine already jumped over the other meeting.
So well then it means we're ready. So thanks again, Ellen. Super interesting talk, much appreciated, and we'll look forward to connecting soon. Thank you.
Okay, thanks everybody.
Bye-bye.